Hello everyone, this is Poornima Deepthi working as an assistant professor in the Department of ECE at MLR Institute of Technology. So today's video we can see the instruction set of 8051 microcontroller and specifically the arithmetical instructions of 8051 microcontroller. So this video is a part of series microprocessors and microcontrollers. In this particular instruction set I have already covered the topic data transfer instructions in the previous video. Do watch that before seeing this arithmetical instructions of 8051 microcontroller. So coming to the overview of today's presentation. So how many types of instructions are there in 8051 microcontroller, and in specifically how arithmetic instructions can be written in 8051 microcontroller. Apart from the general arithmetic operations, what is the importance of DAA, decimal adjust accumulator? So going to the topic, instruction set of 8051 microcontroller. Based on the operations they perform, I've been categorized these instructions into 5 different types. The first one is data transfer instructions, and the second one is arithmetical instructions, logical instructions, and bit manipulation instructions, program branching instructions. In today's presentation, I'll be explaining the arithmetic instructions of 8051 microcontroller. So why we need to use these arithmetic operations? To perform any simple operations or any calculations or anything, we've been using these arithmetical operations. In this particular arithmetical operations, there are 4 different sets are there. The first one is addition operation, the second one is subtraction operation, and the third one is multiplication operation, and the fourth one is division operation. Apart from these operations, there are another important thing is there, DAA, decimal adjust accumulator. So coming to the first general operations, it is an addition operation. So to add two 8 bits of data, we've been using this addition operation. Here in this particular thing, the direct immediate data can be added to the data present in the accumulator. So what will be the operation? The operation is we are having the accumulator. After performing operation, accumulator, the data A will be added to the data immediate data 25H. So in this particular thing, 2 8 bits of data can be added by using ADD. Add is a mnemonic present here. So by using not only direct data, you can add the data present in register with the accumulator, or you can add the data specifically mentioning by using the address and with the accumulator, or indirectly specified by the address and with the accumulator. So these are the general addition operations. The second addition operation is that add C. So here the addition will be performed by using the carry of the carry. So carry will be added to. So here the accumulator output will be like A plus the data 40 along with carry. If carry is set, if carry is 1, that particular carry will be added to the output. So it may be the direct data, or it may be defined by using the register, or you can directly saying using the address location, or indirectly specifying the address location. So here the same operation will be there by using SUBB, subtraction by using the borrow method. So here in this particular thing, the accumulator A will be having A minus hash 13 plus carry. The carry will be added to the original data, and that particular thing will be subtracted from the data present in the accumulator itself. So let's going with the examples here. Let's see the examples here. If we want to add, suppose if the operation is like move A comma hash 40H. Okay. So add A comma hash 30H. Suppose if these two instructions are there in the program. So now after performing this first instruction, the accumulator A will be loaded with 40H data. And after using this, what it will do? So addition operation is there. I didn't mention the carry. So a general addition will be used. So 40 will be added to 30 and output will be 70H. Right? But the thing is here we are using the C, carry. So before adding the 30 to 40, the carry will be added to the 30. So here add 30 is there. So if I am writing add C over there, so 40 will be added with 30, but before adding 30, the carry, we need to check the carry flag. If carry flag is high, that 1 will be added here and it will become 31, and now the general operation addition will be performed. So why we are using this particular carry? So add with carry. Why we are using this one? So add with carry is used when we are performing multi-byte addition. Suppose the carry performs the next byte operation. Suppose I am performing 16 bits operation, 16-bit addition. Though here the general purpose registers won't hold the 16-bit data, so I will be taking like A will hold the highest data and B will hold the lowest data. So now I was performing addition operation with B. Now I have generated the carry. That carry will be, suppose C, I want to perform 7165 added with 8796, right? Suppose here if I want to perform this particular operations, exactly there will be the carry over here, right? Suppose if this is 7. So 9 plus 7 here, 6 plus 5, 11. Though this is the hexadecimal operations, 11 will be represented as B. So now 9 plus 7, it is 16. We can't represent 16 by using normal decimal number. So we will be using 0. 16, 1, 6 will be represented in hexadecimal as 1, 0. So 0 with carry. Now by using 8-bit operations, I have been taking this, right? Here the carry is there. I need to add this carry to the previous this one to get the perfect output 16-bit. So here that's why we are using, if we want to perform multi-byte addition, this carry makes prominent role for the addition operation here. If we didn't took this carry, the output will always be wrong, right? So that's why to perform multi-byte operations, we've been using the carry operation. So to perform that type of operations, there is an instruction like add C, addition with carry. Okay, so the same operation will be for the borrow operation also, for subtraction also, multi-byte operation, we will be taking it as a borrow. So that's why we will subtracting the carry before adding it to the, before doing the subtraction operation. So coming to this one, so subtraction operation also you can give the operation in address, or you can mention it is in direct method. So coming to the multiplication and division operation. So in multiplication operation, there will be specific mul AB instruction only. The data which you need to perform multiplication should always be stored in A and B registers. Suppose if the data we've been using in multiplication operation, 8-bit registers are 99 and FF. Yes, you can multiply with the hexadecimal number. Yes. If we are performing this operation, there is a high chances of getting more than 8 bits of data. If we are performing this operation, yes, high numbers are there, so we will get more than 8 bits of data. So how to store this output? Where we can find the total output? Suppose if we are multiplying with this, we are getting any 16 bits of data. So usually the accumulator will hold only 8 bits of data. So the other 8 bits of data, where can we find? So in this particular AB register, so particularly for multiplication and division, B registers are used. So every time it should be like that only. You should use A and B registers along with for multiplication and division operations. So in this particular thing, the result will be stored in A and B. Okay, for multiplication operations, so we are getting more than 8 bits of data. So that's why we are using 2 registers to hold the 16 bit of maximum. It could be the 16 bit. So that's why 2 registers will be used to store the data. Okay, fine. So for division operation, yes, for division operation, we are getting 2 outputs. One is the coefficient and another one is the remainder. In some operations, remainder holds a prominent role. That's why in this particular 8051 microcontroller, the output coefficient is always stored in A register and the remainder always stored in B register. So these are the 2 particular formats which should follow by using in 8051 microcontroller. Coming to the next general instructions, DEC means decrement. This decrement operation is used to minus 1. So if the operation is like decrement A, if the data before decrementing the data is 40H, now after what will be the data? So after A will become A minus 1, right, decremented by 1. So 40 minus 1, what it will become? 39. So it is decremented by 39. So this particular thing we can use for looping operations or to decrement automatic operations like that. So not only accumulator, you can decrement the data by using the register, you can decrement the data present in the register, and by specifically mentioning the address, you can indirectly specify the address to decrement also. The same opposite will be happen for increment operation. Plus 1 will be done by using increment operation. Only one bit will be increased. So increment accumulator, increment register, increment direct, increment indirect data also. So this is the one of the example for subtraction. So here example is SUBB A comma. So what it will perform? A will be having A minus 20 plus 1. So borrow will be subtracted from the data source operand. So destination operand. So here A is before performing the operation, the A is having the data 35. So here what it will become? 35. A is holding 35 minus 20 plus 1 or 21. So what will be the output? If carry is there, we will be adding 1. If carry is not there, then it will be 0. Suppose in this particular instruction, see, move A comma hash 40H. Okay. Next, A comma hash 20. So is these two programs will hold the same output? No, not necessarily. Why? Because see, if carry is there, that if we are performing any subtraction operations, if borrow is there, then only carry is generated, right? So if there is no borrow, nothing to minus from the original data. That's why here I have taken the another example where clear carry. Here this instruction will carry, if any is there, it will clear the carry data. So here in this one, first instruction A will become 40H, and in this second instruction carry will be 0. Now after subtraction, what will be the data? So 40 minus 20 plus carry is not there. If carry is not there, 40 minus 20 plus, you should add carry. You should add carry. Here the carry is 0. So 0 will be added. 40 minus 20, what will be the output? 20. So this is the difference before having the carry or after having the carry. Okay. So these are, as I already told you, like arithmetical instructions, these subtraction instructions will be used, particularly SUBB, borrow instructions will be used for multi-byte subtractions. Coming to the next one, the last set of instructions in 8051, arithmetical instructions. So increment, you can use increment DPT or increment PC program counter also. And the last one, but very, very important one, is DAA instructions. These are decimal adjust accumulator after BCD. So why this instruction? Why we need this particular instruction? Okay, let's see. I want to add two BCD numbers. BCD means binary coded decimal numbers. So after adding binary coded decimal number, I want suppose I want to design a digital clock. In that particular digital clock, suppose 12:45 PM. This is the time I wanted in the digital clock. Okay, fine. So usually we'll take the time. If to particular, here 12 is there, but this is the BCD number, binary coded decimal number. But we are using 8051. In this particular 8051, the number system is hexadecimal number system. So to represent 12, we've been using C, right? C. So, but human normal, I want the decimal system. So how we will do? So after performing arithmetical operations, if I want the BCD normal number, so then we will use this decimal adjust accumulator. It will adjust the accumulator to the decimal BCD numbers, normal binary coded decimal numbers. So how it will perform, how it will add. So let's see, in this particular thing there are 4 cases. The first one is first performing how this 8051 perform this decimal adjust accumulator. It is having 2 rules. We need to follow these 2 rules. First one, after performing the addition only we can use this DAA. So after add or add with carry, anything after addition instruction we will be using. The first rule is after performing the addition, if it is greater than 9, the lower nibble of A accumulator is greater than 9, the first condition, or the auxiliary carry. So when this auxiliary carry will be there, so if it is generating carry in the lower nibble, so if the lower nibble is greater than 9 or it is generating the carry like auxiliary carry, then what we need to do, we need to add 06 to the accumulator. Okay. The second rule is if the upper nibble, so upper nibble is having, after correcting the lower nibble, we need to check the upper nibble. If the upper nibble is also greater than 9 or it is having carry is there. So for lower nibble, the lower nibble is greater than 9 or the auxiliary carry. After adjusting the lower nibble, we will be moved to the upper nibble. Now if the upper nibble is greater than 9 or it is having the carry signal, then we should add 60H to the output. So let's see the first case. The first case here, after performing this instruction, move A comma hash 21H, as we already know that the accumulator will be loaded with the data 25, right? It is a BCD data. Okay, fine. So next add A comma 12H. So add A comma 12H. So it will be 12H will be added to the accumulator. So A, what now A will become? The accumulator is 25 plus what we should add? 12. So what is the output? 7, 3. So 37H is there, which is the BCD. So here if you check, the first one, the lower nibble is 7, not greater than 9, right? And no auxiliary carry generated while doing the addition. So the first rule satisfied. We will check the second rule. After performing the addition, the upper nibble is not greater than 9 or it didn't generate any carry. By using 2 plus 1, we didn't generate any carry. So there is no carry or anything. So this is the particular output. There is actually no need to check for DAA, right? This is the first case. Let's see the second case. In this particular case, what it will become? A is holding the data 29H. So 29H will be added with 15H, right? Yeah, perform. So 9 plus 5, what is 9 plus 5? Usually it is 14, but here in hexadecimal, how we will represent 14? As E, right? So now 2 plus 1, 3. See, now here DAA is there. So the first rule, we need to check the lower nibble. Yes, we will check the lower nibble. Yes, the lower nibble is greater than 9. Yes, greater than 9. So here the rule breaks. So what we should do? We should add 06, right? Yeah. So 3E, for 3E we are adding 06. So what will be the result? 14 plus 6, 20. Usually it is 20, but the thing is how we will represent 20 in the hexadecimal number system? Yes, 14, right? So here 4 and the carry, right? Now 3 plus 1, 4. So what is the output? 4. Auxiliary carry we got, but the thing is already we have added 06. Now what we need to do? We need to check the upper nibble. Yes, the upper nibble is having 4. Is there any carry? No, carry is not there. This is auxiliary carry, right? So carry is not there. So the output is 44H. See, 29 plus 15 is 44 in BCD, right? This is how the DAA will work. So let's see the another case. Here, what? A is holding data 65 and we need to add 35 to this. So while performing, yes, 5 plus 5, it is 10. So we will represent in hexadecimal as A, and 6 plus 3, it is 9. See, first what we need to do? We need to check the lower nibble. Yes, lower nibble is greater than 9. So what we need to do? We should add 6 to the lower nibble, right? 06. So this is 10 plus 6, 16. How we will represent 16 in hexadecimal number? 0, and carry, right? Now 9 plus 1, how much? Yes, 10. 9 plus 1, 10. Right? 0 will be there, and so sorry, 10. How we will represent 10 in hexadecimal number? A, right? Again, so lower nibble has been solved, but the thing is upper nibble is having greater than 9. What should we do? We need to add 6, right? Again, this is 0 plus 0, 0. A is 10. 10 plus 16, it is 10 plus 6, it is 16. How we will represent 16 in hexadecimal number? 0 with carry 1. So this is the carry. So total how much? 100. We should take carry. So total how much? 100. By adding 65 with 35, we usually get 100. Right? This is the third case. Let's go for the fourth case. So here the number BCD. So the number BCD is A equals to what A is having? 59. So now we are adding A with 48. Okay. So now 9 plus 8, how much is 17? So how we will represent 17 in hexadecimal number? 1, 1, right? Now 5 plus 4, 9, 9 plus 1, 10, 10 will be represented as A. What is the first case we need to check? We need to check the lower nibble. So what is the lower nibble here? No, not greater than 9. But the thing, you need to check the auxiliary carry. Is there any auxiliary carry? Yes, the auxiliary carry is there. The carry which is generated after performing the nibble operation is auxiliary carry. Yes, auxiliary carry is present. So after presenting the auxiliary carry, what we should do? We should add 0, 6. Add. So 7 and A. So now check with the upper nibble. What is the upper nibble here? A. Yes. What should we do? We need to add 6, 0. So what will be the 7? Here A plus 6 is 16. So 16 will be represented as 0 along with carry 1. Right? So 107, which is nothing but 107. If we are adding 59 with 48, we will get 107 as a BCD output. So this is why we are using DAA after performing the addition operation. So if you want the BCD as the output, then we will perform this decimal adjust accumulator. Okay. So until now I have discussed the arithmetic operations present in 8051 microcontroller, and one of the important thing is DAA, decimal adjust accumulator. So thank you.